You are watching one of a series of videos giving an introduction to Orcaflex. The first 4 of these videos, which we've called the fundamentals, are those that we would regard as prerequisites for looking at any of the other subsequent topics. If you are already familiar with these fundamentals, you may want to pick and choose the subsequent videos you watch based on your area of interest. If you're a complete beginner with Orcaflex, I would strongly encourage you to watch the full series in order, as this will give you a good basic overview of the program, how to navigate it, and where to access and input data. It goes without saying that the quality of any Orcaflex analysis is only as good as the quality of the input data, and that, of course, relies on the skill and experience of you, the user. These videos will help you to learn how to use Orcaflex as one of your analysis tools, and I do hope that you find them educational and maybe even a little bit enjoyable too. This video will focus on the shape object and the various contact models available to us in Orcaflex. Firstly, it is important to remember that not all objects in Orcaflex are permitted to contact each other. Lines can contact the seabed, elastic solid shapes, supports, and other lines via the line clashing and line contact models. In addition, 3D and 6D buoys can contact the seabed and elastic solid shapes. Examples of contact which isn't modelled in Orcaflex include vessels with lines, vessels with other vessels, vessels with elastic solid shapes, and elastic solid shapes with other elastic solid shapes. The first contact relationship we will look at is line and shape interaction, and as part of this we will now be introduced to the shape object. Orcaflex shapes are simple 3-dimensional geometric objects that can be fixed in place or connected to other objects and are most often used as contact surfaces. There are a number of geometric shape options to choose from, and when we look at the data form we can see these listed in the shape menu. Cylinder is the default, with additional options for plane, block, and curved plate. The plane option extends a plane to infinity in 2 directions. The angle and direction of the slope of the plane can be adjusted. The block shape is a rectangular cuboid, and on the geometry page of the data form we can specify values for x, y and z, representing the length, width and height of the cuboid. The origin of these dimensions is at one corner of the block. The cylinder is a thick-walled hollow pipe defined by its inner and outer diameter, its length, and the azimuth and declination of the axis. The final geometric shape option is the curved plate. These shapes are particularly suited to modelling bell mouths, but can be used to create any revolved profile. The overall shape is given by a table of diameter or radius against distance along the shape's principal axis. The curved plate can be solid, or, if the option is ticked, it can also be hollow. If hollow, it has inner and outer surfaces, both of which will be treated as contact surfaces for the elastic solid shape type. The curved plate is assumed to be a fully revolved solid, but this can be changed by reducing the included angle of revolution from the default value of 360 degrees. Looking now at shape types, there are a number of options to choose from in the Type menu. Elastic solids are used to model physical barriers to lines, 3D buoys and 6D buoys. They have a stiffness specified on the stiffness and damping page, and resist penetration by applying a normal reaction force to the line or buoy. For lines, contact occurs with line nodes, and for buoys, with their vertices. Friction can also be generated through the use of a friction coefficient, specified on the friction coefficients data form, which can be found in the model browser here. It should be noted that friction for contact with elastic solids is only included in dynamic simulations and not in statics, unless working with static restart models. Trapped water shapes are used to model areas where fluid motion is suppressed, such as a moon pool or the inside of a spa. Inside a trapped water shape, the fluid motion is calculated as if the fluid were moving with the shape. Drawing shapes have no physical effect on a model and are just intended for drawing objects of interest. For example, a drawing shape might be used for the representation of a ship's bridge or some other structure which has no effect on the model but is needed to aid visualization of the system as a whole. The final shape type is the label. These have no geometric shape or physical effect on the model and are used to draw arbitrary text labels on the 3D view. Whilst not strictly speaking a shape, they are included in the shape object as this is the object most commonly used purely for visualization purposes. If attached to an object, the text in a label will move with that object and will be shown horizontally in the wireframe view. Let's take a new model and place a vessel in it. We'll also insert a shape and connect it to the vessel. And on the data form, change its type to label. Now on the labels page of the data form, we can add a label or multiple labels and specify the label's position, its colour and alignment, and the actual text itself. Note that a line break can be used in the text using the sequence \n. Now when we run Dynamics, we see the label moving with the vessel, but remaining in the horizontal orientation regardless of the orientation of the view. Note that the text label is not visible when we switch to the shaded graphics view. Moving back to the elastic solid shape type, we will spend some time now looking at line and shape interaction. As previously stated, if we want to model contact with a shape, we need to use the elastic solid type. When a node is within the boundary of an elastic solid shape, a reaction force pushes the node towards the nearest surface. Let's look at this in practice by building a simple model. First, we'll place a shape into the model. You'll see that the default cylinder geometry is used initially. On the data form, we'll change the shape to a block. To provide a larger surface for our contact, we'll modify the X size to 50 meters. Next, we'll position the block at the global origin 0, 0, 0. Now insert a line into the model, and the only change we will make is to position the ends, with end A fixed at -10, 0 and 45, and end B fixed at 60, 0, 45. In the reset state, the line is hanging through the shape and there are 3 line nodes within the boundary of the shape. Let's run statics and see what happens. Okay, not a lot. 2 of the line nodes have changed colour, indicating that they are experiencing contact, but the line isn't being lifted up as expected. There's an error we have made here which only becomes obvious when we change the view orientation. Control Q rotates the view by 90 degrees, at which point we can see the block has not been positioned correctly in the Y direction. The line is hanging at the back side of the shape. We'll reposition this by setting a Y value for the shape of -10. This results in the line hanging through the centre of the shape. Now when we go back to the default view and run statics, the line gets lifted up as expected, with 5 line nodes now coloured white, indicating contact. It is often helpful to look at a system from multiple directions, particularly when trying to diagnose an issue. Remember that you can have multiple views open at the same time. Go to the toolbar and Add 3D View, or use the Ctrl+3 keyboard shortcut. You can now rotate one of the views. Remember, Ctrl+Q will rotate a view by 90 degrees, and you can then look at both views simultaneously. I mentioned earlier that a linear reaction force is applied to nodes to move them to the nearest surface. We need to take care that the nearest surface is the one we intend the contact to be modelled for. As an example, we'll move end B of this line slightly and rerun statics. On the line data form, we'll modify the NB values to 75, 0, 30. Now, because of the long segmentation, we have 2 nodes in contact on the top of the shape and 1 in contact on the side of the shape. For this reason, we have to be very careful when modelling contact close to sharp edges like this, as a small change in position of a node could result in a large change in reaction force, magnitude and direction as the contact moves from one surface to another. Another observation we can make about this model involves the fact that the contact between a line and a shape occurs only at the line nodes. We need to make sure, therefore, that the distance between the nodes, i.e. the segment length, is small compared to the dimensions of the shape. Whilst the sharp corner is still a potential issue, using a smaller segment length would go a long way to improving the line-shape interactions here. Let's open the line data form and reduce the segment length from the default 10 meters to 1 meter. This leads to a greater number of nodes and an improved resultant contact relationship. If we zoom in on the corner of the shape, the line still appears to be hanging through it, with 2 nodes of particular concern. Consider the fact that the nodes are modelled as spheres for contact purposes, and contact therefore occurs at the outer diameter of the nodes. If we use the measuring tool, we can see the depth of penetration of the left-hand node is approximately 0.3 meters. The closest surface to the right-hand node is actually the side of the shape, and its depth of penetration is around 0.2 meters. The forces acting to push the line into the shape at these nodes are not being overcome by the reaction force being applied by the shape to push them out to the surface. One of the judgments the analyst has to make is whether the depth of penetration of the line nodes into a shape are realistic. If the shape was representing a hard surface such as steel, this depth of penetration would not be realistic. To reduce this depth of penetration, we need to increase the reaction force pushing the line nodes out of the shape. The magnitude of the reaction force is directly affected by the normal stiffness on the shape data form. The normal stiffness can be a linear value, the reaction force that the shape applies per unit depth of penetration per unit area of contact. Alternatively, the presence of a small down arrow to the right of the normal stiffness value indicates that it can also be a non-linear value. In this case, variable data can be used to define a data set for reaction force per unit area of contact against depth of penetration. Note that there is also a shear stiffness value on this page. This doesn't impact the depth of penetration, but is used for the friction calculation. It will only influence the behaviour of a line in contact with the shape if a friction coefficient is also defined on the friction coefficients data form we saw earlier. You can find more information about the friction calculation by navigating to the documentation while on the stiffness and damping page of the shape data form. In the shear stiffness section, you can then follow a link to the friction theory page. To reduce the depth of penetration, let's increase the normal stiffness from the default 100 kilonewtons per meter squared to 5000 and run statics again. Now we see a much smaller penetration of the line nodes into the shape, but we still have the node on the right in contact with the side of the shape and the node on the left in contact with the top of the shape. This once more highlights the potential for issues when a line contacts a shape at a sharp edge. If there is any lateral movement in the line at this point, we will see noise in the simulation, as nodes are either pulled up onto the top of the shape or fall off the side. Remember once again that these nodes are modelled as spheres for contact purposes. We've seen that increasing the normal stiffness of the shape reduces the depth of penetration of a line into the shape, but don't be tempted to try and set real-world stiffness values, as this can lead to numerical instability. For a global analysis package like Orcaflex, the small changes in response from very high stiffness values can usually be regarded as insignificant. In fact, if you are concerned with sub-millimeter accuracy on shape penetration, then a global analysis tool like Orcaflex probably isn't the right package to be using. I want to take a look at line-shape interaction further using a cylindrical elastic solid shape. The aim is for the line to solve lying over the top of this cylinder. We're reminded with this model that line nodes are always pushed to the nearest surface in statics, and that surface may not be the desired surface. Here we have a cylinder which has a non-zero inner diameter, meaning there is an inner surface. When statics is run, some of the nodes are pushed to this inner surface, leading to a mathematically correct but clearly unrealistic solution. The easy solution here should be to remove the inner surface by setting the inner diameter to 0, as it isn't needed in this case. Actually, as we can see from the static solution, it isn't quite that simple. We want the line to solve over the top of the cylinder, but the line nodes are being pushed to the lower part of the cylinder outer surface, that being the nearest surface for the nodes. The model solves statics with the line nodes embedded inside the shape, because the reaction forces pushing the nodes down are not large enough to overcome the line's axial stiffness. So, how do we resolve this model so that the line solves as intended over the top of the shape? We're going to use the spline starting shape for step 1 of line statics. We've seen in previous videos that this provides more control over the starting point for line statics. And in combination with the magnitude of standard error, magnitude of standard change convergence control method, we reduce the magnitude of the iterative steps taken in the line statics calculation, thereby improving the ability of the line to solve in the intended position. Note also that it's been necessary to reduce the magnitude of standard change slightly so that the iterative steps are small enough for line statics to solve. Moving on now, and we're going to look at a slightly more realistic model, that of a cable being deployed over the stern of a vessel. We'll start by introducing three objects into a new model: a vessel, a line, and a shape. These will be set up and positioned using the information in this table. First of all, we'll position the vessel at the origin by setting its position to 0, 0, 0. All other vessel properties can be left at their default settings. Next, we'll adjust and position the shape. It will be the default elastic solid type, as we need to model contact. We'll choose the block shape with a size of 95 by 20 by 10 meters. This will be connected to the vessel at a position of -50 in X, -10 in Y, and -3 in Z. As you can see, this positions the shape at the top of the vessel and is intended to represent the deck. We'll therefore rename it accordingly. The intent here is to model a cable lying along the deck of this ship and hanging over its stern. We need to include an elastic solid shape in the model to represent the deck of the ship because, as we heard earlier, lines don't interact with vessels. Moving to the line types data form, we will stick with the default general category. I'll set the outer diameter to 0.08 meters, the inner diameter to 0, and the mass per unit length to 0.015 tons per meter. And finally, the bending and axial stiffnesses to 1.5 kilonewton meters squared and 120 E3 kilonewtons respectively. All other line type properties can remain at their default values. We'll now make some adjustments to the line. Firstly, on the structure page, the length should be 230 meters. Then we will connect end A to the vessel at a position of -30, 0, 7.04. The rather precise Z value used here takes into account the diameter of the line, so as to ensure the base of the line is level with the top of the elastic solid shape representing the deck. We will anchor end B at a position of -200, 0, and then because it's anchored we can set a height above seabed of 0. This height above seabed automatically applies a Z value of 0.04 above the seabed, so that's automatically taken into account the diameter of the line. Now when I try and run statics, there's a warning referring to something called the lay azimuth. The first thing to note is that this is a warning, not a program error or a simulation failure. It is still possible to click OK and ignore this. However, we provide warnings for good reason, and will usually give additional information to help understand the warning, as we have here. If we click on the More Details link, this opens up the help file, and we're taken to a page in the documentation about line statics, and specifically the application of seabed friction. If we take a look at the statics section of the line data form, we see a lay azimuth value which is 180 degrees by default. The lay azimuth value is used in statics to indicate the direction in which the line was laid and towards which friction acts. We need this because friction is a dynamic phenomenon and we have no history of motion in statics. Looking at our model, the line is laid from left to right in the positive x direction, which would equate to a lay azimuth of 0 degrees. We could adjust this manually, but in most cases we wouldn't know what the value should be. But we have a set lay azimuth button on the line data form which calculates the correct value based on the horizontal direction from end B of the line back to end A. If we press this, we'll get a value of 0 in this case, as predicted. Having run statics, we've clearly not managed to achieve the design intent, with the line instead solving through the deck shape. Remember that line nodes will experience a reaction force during statics that pushes them to the nearest surface of an elastic solid. Because the line is hanging through the shape in the reset state, the second node is pushed to the bottom surface of the shape, leading to this unrealistic solution. What if we just had more nodes? Let's reset the model and try 1 meter segmentation and see if that improves things. As you can see, we still have a problem with the line stuck through the shape, except there are now a number of nodes coloured white, indicating contact. The solver is, once again, trying to push these nodes to the nearest surface, but the reaction forces applied to the nodes are not enough to overcome the axial stiffness of the line. As we found with the model of the line and the hollow cylinder, we can use the spline starting shape to ensure the line starts the full static stage in the correct place above the deck, thereby making contact with it once gravity takes over. So let's open the line data form and change the step 1 statics method from catenary to spline. And on the spline starting shape we can adjust the spline control points such that we have the spline curving over the deck and down to the seabed. On the spline starting shape page we can use the following coordinates for the spline control points. If we run statics again, we see this doesn't appear to be much better, with the line still solving through the deck shape. This is a good time to try the magnitude of standard error and magnitude of standard change convergence control method. But with the default settings, still no improvement. OK. Final change. We'll reduce the magnitude of standard change from 0.2 to 0.01. This now solves correctly over the stern of the vessel. Having said it has solved correctly, if we zoom in we can see that isn't strictly true. The line hangs over the stern but has been pushed into the shape on the top edge. We have discussed earlier the potential for problems where lines interact with shape edges like this. The reaction forces acting to push the line nodes out of the shape are not large enough to overcome the forces pulling them into the shape. The reality of this scenario is that a vessel chute is likely to form a large radius here, so there would in fact not be a severe edge present. The shape geometry is fairly simple, so we can't add a radius to this existing block. However, we can add another shape, and the two can then be used in combination. We'll now add a new shape to form the chute. We'll use the data shown in the table to create and position the shape. So this is going to be the default shape, which is the cylinder type. The default length is correct at 20 meters. We just need to change the outer and inner diameters. The outer is 8 meters and the inner is set to 0. We'll connect it to the vessel at a position of -50, 0 and 3. And we'll set the azimuth and declination both to 90 degrees in order to orientate it correctly. When we run statics now, we should expect to see the line lying over the top of the cylinder. However, it appears to just fall straight through. The clue to resolving this issue can be found by looking in a different orientation. We can see clearly in the plan view that the cylinder has not been placed correctly in the XY plane, and in fact needs a Y value of -10 to be positioned correctly across the vessel's stern. So, always check that objects have been positioned correctly in all planes. We'll return to the default view now and run statics. The line now solves over the cylinder, representing the chute, but note the large depth of penetration. If we zoom right in and use the measuring tool, we can see we've got a depth of penetration of approximately 40 centimeters. This is going to be unrealistic with a steel chute, but can be reduced by increasing the normal stiffness of the shape from the default 100 kilonewtons per meter squared to, say, 1000. This is just an arbitrary figure for this quick example. For some analyses, small variations in the depth of penetration in a shape like this as a result of modifying the normal stiffness may have little effect on the results of interest. However, if in doubt, we would recommend performing a sensitivity study with varying stiffness values to ensure that this is the case. At this point, we've only changed the stiffness of the cylinder representing the chute. It may be that we also want to change the stiffness of the deck shape. If we want to change a property on multiple objects, such as the stiffness, we can do this via the All Objects data form. On the All Objects data form, select Other Data and Shapes, and the normal stiffnesses can be modified together by typing the top value, then selecting both values and using the Windows Copy Down functionality. This simple model now solves statics quite efficiently and as intended. It's worth saving it, as it will be used as a basis for further work in a later video about the winch object. So, that was shape contact. We'll now move on to look at how lines can contact each other, with the first example of this, line contact. Line contact is used for applications such as pipe-in-pipe systems, pull-in operations, piggyback risers, and drilling riser choke and kill lines, where we have continuous or consistent contact between lines. Line contact is active in statics, and friction can also be included in a line contact relationship. Line contact data is input on the line contact data form. Since line contact requires lines, this data form is not visible until a line is present in a model. As soon as I insert a line into this model, we see the line contact data form appear in the model browser. You may remember from a previous video that we have a model browser setting called View by Groups, which I have enabled here in the pop-up menu. This setting places the line contact data form within a shared data folder at the top of the model browser. A new installation of Orcaflex will not have View by Groups enabled, in which case the line contact data form can be found within the Lines folder. Opening up the line contact data form, we're presented with two pages, Relationships and Penetrator Locations. The Relationships page is where we define all the line contact relationships we will need in the model. We can choose whether or not they are active, which allows us to create the relationships and then only activate them when necessary, This can be a particularly helpful feature when trying to diagnose convergence issues in a model. Line contact models point to surface contact, and we nominate one line as the penetrating line in a relationship and another line as the splined line. The splined line provides a curved cylindrical contact surface for the penetrators, the points, attached to the penetrating line. There is a choice of 3 types of relationship: inside, outside, and around. In an inside relationship, the penetrating line can be likened to a pearl necklace, the penetrators being the spherical pearls which pass through the inside of the smooth splined line. Alternatively, in an around relationship, the penetrators can be likened to a series of rings which the smooth splined line passes through. Finally, in an outside relationship, the penetrators on the penetrating line make contact with the smooth outer surface of the splined line. When we talk about penetrators, these are by default located at every node on a line. If you wish, you can instead select different penetrator locations by specifying a data set on the penetrator locations page. Once you've created this data set, this can be then selected from the penetrator locations menu. Penetrator discretization is intended to be used where there are lines in a line contact relationship with the same or similar diameters. For example, a centralized pipe where the centralizers are in an interference fit with the outer pipe. This kind of scenario can cause convergence issues because the direction of the contact reaction force is ill-defined, with small changes in position of either line leading to large changes in contact force direction. It works on the principle of discretizing the contact model into a number of smaller penetrators to ensure a better representation of the true physical contact surface being modelled than can sometimes be experienced with a single penetrator. We'll come back to penetrator discretization in a short while by looking at a simple worked example. The Containment Enabled checkbox determines whether or not fluid loads an elastic solid contact on the inner line in this relationship should take account of its containment within the outer line. For example, the contained length of inner line will be shielded from the environmental fluid forces if the checkbox is enabled, and any contact, for example, with the seabed, will be with the outer line. The stiffness values work in the same way as the line-shaped contact model, with the normal stiffness dictating the depth of penetration of one line into the other, and the shear stiffness being used in the friction calculation. A value of 0 for shear stiffness will disable friction. Finally, friction coefficients can be defined in both the lateral and axial directions. We will now build a simple model to help illustrate line contact, using the information in the table on the screen. On the line types data form, we'll create 2 line types, one for the inner and one for the outer line. We'll name them for the sake of clarity. Outer LT and inner LT. Next, on the geometry page, we'll set the diameters. The outer line type will remain the default diameters, while the inner line type has an outer diameter of 0.1 and an inner diameter of 0. Finally, for the line types, on the structure page, the inner line type has a bending stiffness of 1 kN squared, while the outer remains at the default value of 120. We could also optionally change the colour of one of the line types to help differentiate them in the 3D view. The next requirement is to set up the first of the 2 lines, so we'll open up the line data form and rename this one to outer. Next, we'll set the length to 20 meters, and the segment length to 0.5 meters. And the positions for end A and end B to 10, 0, 10, and 10, 0, minus 10 respectively. We now need a second line, so could either insert a brand new line or, as I'm going to do, copy and paste the existing line. The new one is called inner and needs a length of 25 meters and a segment length of 0.5 meters. It also needs the line type changed to inner LT. The positions for end A and end B are 12, 0 and 15, and 12, 0 and minus 10. And end B should be set to free. At this point, the lines are fully set up and we need to create the line contact relationship. We do this by opening the line contact data form from the model browser and adding a new relationship. This will have the penetrating line as the inner, which will be inside the splined line, the outer line. We need a non-zero normal stiffness for the relationship to have any effect, so we'll set this to 5,000 kilonewtons per meter squared. Now if we run statics, we see the inner line drawn inside the outer line. In this model we've opted to use an inside relationship with the inner line as the penetrating line, which means contact is between the nodes of the inner line and the inner surface of the outer line. If we zoom in on the top end of the outer line, we can see an issue with the choice of relationship for this configuration. We can see more clearly in the shaded graphics view that the inner line is penetrating through the side of the outer line, since contact is only made at the nodes of the inner line, the default option for penetrator locations. One workaround for this is to just add more nodes to the penetrating line, reducing the magnitude of the breakout. However, this isn't always a desirable solution, as it may adversely affect the model in other ways. For a model like this, we may find that an alternative relationship provides a more realistic outcome. In some cases, reversing the relationship can also resolve convergence issues. Let's reverse the relationship now and see if we can improve the way the inner line exits the outer. The penetrating line now becomes the outer line, and this will be around the splined inner line. If we try and run statics now, we receive an error message which states that in an around relationship the outer line must include torsion. The first problem. Let's go to the outer line and turn on torsion. Next, we receive a warning that with torsion enabled, it is recommended to have non-zero twisting connection stiffness for at least one end. Ours are the default value of 0 at both ends. The second problem. This is a warning, not an error, which means we can potentially ignore it. It states that there may be convergence problems. However, this simple model is still able to solve anyway, albeit with a little trouble. Let's see if we can improve this by following the advice. And we'll apply infinity end connection stiffness in both twisting and bending. And and this is on the outer line, which has torsion enabled. So running statics again, the warning message has gone, but the line has taken an unexpected shape, and we are seeing some convergence issues now. This reminds us of the importance of setting appropriate line end orientations when using non-zero end connection stiffnesses, the third problem. Turning on the local axes shows us that we have the default line end orientations with the local z-axes pointing vertically upwards. For the yellow outer line, the z-axis should be pointing into the line at end A and out of the line at end B, which means that for both ends we need to adjust the declination by 180 degrees. Running statics again, we see an apparently fundamental issue with the line unable to find equilibrium. We can often resolve this by reducing the size of the iterative steps in the static calculation. We'll try a small increase in line statics damping for the outer line, the first named line in the description as it appears in the statics progress window. This is the first line in the group, as listed in the model browser when viewed by types, that is not a child of any of the other lines in the group. The line statics step 2 policy for coupled systems dictates that this is the line whose convergence parameters will control the line statics calculation. I'll adjust the damping from 1 and 10 to 3 and 30 and take a look at the resultant solve. As you can see, this now successfully solves very quickly. More importantly though, if we take a look at the top end, reversing the line contact relationship has resulted in an improved interaction between the lines at the top of the outer. Note that we do still see a small amount of overlap of the inner line into the outer. This can be reduced further by increasing the normal stiffness in the line contact relationship. When we were introduced to the line contact data form earlier, we briefly looked at penetrator discretization and noted that this can be useful in solving convergence issues sometimes experienced with lines of the same or similar diameter in a line contact relationship. For similar diameter lines, small changes in position of either line can lead to large changes in contact force direction, which can cause instability in the static calculation. We can look at this in practice by making some changes to the line contact model we've just created. Note that penetrator discretization requires torsion to be enabled for the penetrating line, since it involves the creation of multiple penetrators which are offset from the center line. Looking at the outer line data form, we've already enabled this to allow the around relationship to be used. Moving to the line types data form, I'm going to edit the outer diameter of the inner line such that there is a slight interference fit. On the geometry and mass page, I'll set the inner line type outer diameter to 0.251, 1 mm larger than the pipe it is passing through. Now when we run statics, the calculation seems to get stuck before eventually failing. I'll just orientate the view so that we can see the discs representing the line nodes. Note that we have two circles visible for the outer penetrating line. The outer discs represent the contact diameter of the line type, and as this is an around contact relationship, the inner diameter of the penetrating line nodes is used. which is represented by the inner discs visible here. In fact, if I disable this line contact relationship, you'll see the inner contact circle disappear. I'm going to introduce penetrator discretization by specifying a count of 3 and a scale of 1.5 on the line contact data form. This scale can go up or down depending on whether an inside or around relationship is specified. It scales the contact diameter and area, but not the contact length. Using a larger number of discretized penetrators will result in a better representation of the true physical contact surface being modelled, but this has an associated computational cost. For more information about this feature, refer to the penetrator discretization section of this page in the documentation. Discretizing this model changes the single inner contact surface of the outer line into 3 larger contact surfaces distributed evenly around the original contact surface. We now see an immediate solve as a result of the contact surface being more robustly defined. Having created a simple line contact model, we'll go back and take a closer look at a few examples of some applications I mentioned earlier. All of the following examples can be found on our website using the links on screen. Firstly, we have a J-tube pull-in model with a riser being deployed from a vessel, pulled into a bell mouth, and then up through a J-tube. There are 2 contact relationships present in this model. The first of these is the riser inside the J-tube, with penetrators at each node of the riser. The second relationship models the clamping of the J-tube to the tower. This uses an around relationship with the tower as the penetrating line, and 3 discrete offset penetrator locations for modelling the clamps holding the J-tube to the tower. With this example, we can look at the clamp contact force by opening a static state range graph result for the J-tube and selecting line contact force as the variable. Here we see 3 peaks in the graph where the J-tube is clamped to the tower. The next example is a pipe lay model which has a cable piggybacked onto the pipe. Again, this has 2 line contact relationships. The first of these is the pipe around the cable, and this models discrete cable clamps spaced at 5-meter intervals, as can be seen on the penetrator locations page. This utilises the penetrator discretization model to provide a more robust contact model due to the clamp and cable being the same diameter. The second relationship is the cable outside the pipe, and this allows the outer diameters of the 2 lines to contact each other. The final example is a drilling riser, which has choke and kill lines clamped to the riser using around relationships. Further to this, there are 2 inside line contact relationships providing contact between an internal drill string and the riser, and the drill string and the casing below the seabed. Now we'll look at the second example of how lines can contact each other, line clashing. Line clashing is intended for intermittent dynamic contact between lines, such as would occur if 2 free-hanging lines in close proximity were to come together as a result of wave motion, for example. Clashing is shown in this model by affected line segments turning red when they make contact. Contact is segment to segment, and as it is dynamic, line clashing isn't available in statics. Contrast this with the line contact model we just discussed, which is penetrator to spline contact and is available in statics. Another differentiation with line clashing is that it does not include friction. Line clashing is computationally expensive as it requires continuous monitoring of the distances between lines in Dynamics. For this reason, it is enabled on a per section basis, meaning that we can choose to enable it only on sections of line which we are concerned may come into contact with each other. We do this by ticking the box on the structure page of the line data form for one or more sections of a line. The visualization of the contact in the 3D view is determined by the contact options chosen on the drawing page. As well as the checkbox on the structure page of the line data form, we also need to make a change to the default line type data. On the contact page, the clashing stiffness value should be non-zero in order for lines to effectively be pushed apart if they try to pass through one another. As with other contact models, a smaller clashing stiffness will result in a greater depth of penetration. We will now set up a model which includes two lines, one above the other. We will then allow one line to fall and make contact or clash with the other line. The model will be set up using the data shown in the table. Firstly, we will insert two lines into a new model and immediately go to the line type data form and create the first line type. With an outer diameter of 0.15 meters, an inner of 0, and a mass per unit length of 0.5 tons per meter. The only other change to the default line type data is a line clashing stiffness of 10E3. Having created one line type, I will show you how easy it is to create another based on the first. We simply need to select the existing line type in the model browser, then use the standard Windows copy-paste functionality. In this case, the only difference will be the colours, so we'll just go to the drawing page and change the colour for the second line type to green. And I'll change the line type names for clarity. Upper LT and lower LT. Now we can set the data on the line data forms. I'll open the first line and change the name to upper line. Then enter the data as per the table. End A will be fixed at a position of -10, 0, -50, and end B at a position of 10, 0, -50. We'll use the release at start of stage option to allow one end of the upper line to fall, and this will be done at the start of stage 0. The length will be 30 meters, and we'll use a segment length of 1 meter. I need to remember to tick the clash check option on the structure page. In order to set the next line, I can move straight to that data form by clicking on Next at the bottom right, or by pressing the F6 shortcut. Again, I'll change the name, this time to lower line, and I'll input the data on the form. This one will be fixed at 0, 15 and -50, and at NB it will be at 0, -15, -50. The length will be 40 meters with a segment length of 1 meter. Again, I need to make sure the clash check option is ticked, and I also need to remember to change the line type for this line to lower LT. Finally, for this model, I'll go to the general data form and set the time step to 0.02 seconds on the Dynamics page. Now, when we run the simulation, we should see one end of the upper line released at the start of dynamics, allowing it to fall and make contact with the lower line. We can see, having zoomed in on the contact point, that the segments which are experiencing the clash contact are coloured white. The drawing of this contact can optionally be turned off on the drawing page of the line data form. I would like to make a change to this model now to demonstrate the consequences of having a time step that is too long in a simulation with a high frequency event. First of all, I'll use a workspace file to give me two views of the lines in wireframe and shaded graphics. Let's reset the model and open the general data form, and on the dynamics page we'll change the time step to 0.2 seconds and then rerun dynamics. This time step is deliberately longer than usual to intentionally create an undesirable result. Now when we run the replay, we see the upper line falling through the lower line as if it wasn't there, with no contact being modelled. This is despite the clash check option still being ticked on both line data forms, and the line clashing stiffness still being a non-zero value. I'll move now to a second workspace file giving us a close-up view of the expected contact point. If we advance the replay one frame at a time, which is done using the Ctrl-A shortcut, we can see that as the yellow line falls towards the green line, and just before it hits it, we are at a time of -7.2 seconds. If we advance to the next time step, -7 seconds, you can see the yellow line is now below the green line, so consequently no contact has been observed. So, if we have a model where there are high frequency events, such as lines clashing or objects being released, we must make sure the time step is short enough to capture these. We'll revisit the model again and reduce the time step to 0.1 seconds. Now, having run the replay again, we can see there is some contact occurring, but the yellow line appears to break through the green line. At -7.2 seconds, the yellow line is above the green line and no contact is yet observed. Then at the next time step, -7.1 seconds, contact is made. You can see the white segments on both lines indicating this. However, we can see that the yellow line is now below the green line, with contact then being lost at the next time step, -7 seconds. So, the lines were in contact, but then that contact was lost. Why did that happen? We'll use a simplified model to try and answer that. This uses two short lines, both with clashing enabled, in order to model the contact between them. This time the upper green line is driven down in a controlled manner using a constraint. The constraint and how to use it is the subject of a later video. Let's run a replay and watch what happens. You can see the upper green line starts to move down, and when it makes contact with the lower yellow line, the line segments turn grey where the contact is occurring. At this point, the green line starts to penetrate into the yellow line, while at the same time deflecting it down. The depth of the penetration of one line into the other is determined by the line clashing stiffness. This has been set deliberately low in this example to help illustrate the breakthrough effect. If we move to a wireframe view and watch it again, we can see the contact from a different perspective. We need to remember that when contact between two objects occurs, a reaction force will be applied to push them apart. The magnitude of that reaction force will depend on the contact stiffness and the depth of penetration. As the green line makes contact with the yellow line, a reaction force is applied downwards on the yellow line to deflect it to the nearest surface of the green line, which is the bottom surface. There is an equal and opposite reaction force acting upwards on the green line, pushing it towards the top surface of the yellow line. So far so good, and we are seeing behaviour that we would expect, albeit with an exaggerated depth of penetration for the sake of the illustration. The current time step of this model is 0.01 seconds. Now let's see what happens if we choose a slightly longer time step, say 0.05 seconds. To do this, I will reset the model, open the general data form, and change the value on the dynamics page here. After running the simulation, we now see the green line moving down and the yellow line being deflected as before, but at a certain depth of penetration, the green line suddenly appears to break through. Let's stop the simulation and move to a specific time step, 8.05 seconds. I can do this by clicking on the small triangle next to the replay pause button and entering that value. Now, if I zoom in, we can see the upper line is almost fully embedded in the lower line, but its centre line is still above that of the lower line. This means that the reaction forces will still be applied downwards on the lower yellow line, deflecting it down. If I advance to the next time step, 8.1 seconds, the upper line has penetrated the lower line so far that its centre line is now below that of the lower line. This means the direction of the reaction forces has now reversed, pushing the yellow lower line above the upper green line, creating this breakout effect. This has occurred because, with a longer time step, the distance between node equilibrium positions is greater. Consequently, the green line centre line has, from one time step to the next, moved far enough that the yellow line centre line has effectively swapped sides and is therefore no longer being correctly modelled. Moving back to the previous model, that is exactly what happens here. The time step is too long to capture the upper yellow line falling and being stopped by the lower green line. At -7.1 seconds, contact is made, but the yellow falling line is below the green stationary line, so it has a reaction force pushing it down, which means that at -7 seconds it has continued down, at which point gravity takes over. The point being made is that we need a small enough time step that will allow this kind of interaction to be accurately observed. If the time step is so long that the falling line falls below the centre line of the lower line between time steps, that is when you will see this breakthrough effect. Finally, we'll return the time step to the value we used at first, 0.02 seconds. And then rerun the simulation. With another workspace file which shows the full model, we can now see we're back to the expected behaviour. The last contact model we will look at in this video is supports. Supports are available on the supports page of both vessels and 6D buoys. They are active in statics and dynamics, and the contact is enabled by selecting one or more lines to be treated as supported lines. The contact model is line segment to cylindrical penetrator and is similar to the spline penetrator line contact model. The supports feature was developed originally to provide a more efficient means of creating pipelay models, with a specific contact model for the purpose of simulating pipelay rollers. The generic name supports was chosen as it became clear early on in the development that this feature would be more widely useful than just for modelling pipelay rollers. One of the key benefits of the supports feature is what is known as a desired side. Each support cylinder has its own axis system, and the solver knows that the line should always be positioned in the positive Y direction, the desired side. This typically leads to much more robust convergence than attempting to use other means of creating pipe lay models, such as line contact or elastic solid contact. We'll focus now on the main use of supports in pipe lay analysis as we build a simple example model with a pipe deployed over a stinger. With a new model, let's introduce a vessel and a line. We'll then build the initial model using the data in this table. The vessel will use the default properties and be placed at the global origin. For the line type, set the category to homogeneous pipe, then an inner and outer diameter of 0.25 and 0.22 respectively. This will be a steel pipe, and the default values for Young's modulus and material density are suitable. All other line type properties can be left at their default values. Finally, for the line data, we'll set a length of 500 meters. End A will be connected to the vessel at -30, 0 and 10 meters. And end B will be anchored at -500, 0 and with a height above seabed of 0. Before moving on to look at the supports, note that when statics is run, we see a lay azimuth warning. As we've seen in a previous video about the line object, this relates to the application of seabed friction in statics. You can find more information about this by looking at the line object video and also by clicking on the More Details option in the warning. We resolve the lay azimuth warning by opening the line data form and pressing the Set Lay Azimuth button in the Statics section at the center right. The lay azimuth in this case should be 0 degrees, the horizontal direction the line was originally laid from the anchored end back to the vessel hangoff. Now, when statics is run, we see the warning is gone. The next step is to build the supports which will represent the stinger. For this we will use the data in this table. As with lines and vessels, supports have two separate layers of data. Firstly, the data for specific instances of supports in a model found on the supports page of a vessel or 6D buoy. Secondly, the data pertaining to specific types of supports, such as U or V-shaped supports. This data is found on the support type data form, accessible either from the vessel or 6D buoy or from the model browser. Note that you will only see the form in the model browser when the number of supports is increased from the initial value of 0. The first step is to set the geometry specification. The default specification is explicit, which allows each individual support to be positioned and orientated independently via the support coordinates page. In our case, we will use the simple specification, which allows a path to be drawn along which the supports will be positioned. Having selected the simple specification, we will add a support path section. By default, support paths have a bend radius of infinity. This means the path will form a straight line. We'll assign it a length of 70 meters and a bend radius of 80 meters. You should see the support path being created dynamically in the 3D view. Initially, the support path begins at the vessel origin, which is undesirable in this case, so we'll change this to -40, 0 and 7. We now need to input the 8 supports, starting at 0 meters with a 10 meter spacing. This is a good example of the use of Excel for efficiency of data entry. Moving over to Excel, I can quickly create a list of arc lengths using the ability in Excel to copy data down to form a list. This list can then be copied over to Orcaflex using the standard methods. The final step here is to introduce a Z offset to optionally lift the supports away from the path. Again, Excel functionality is useful here, as I can set the value for the first support and then simply copy the data down using the shortcut Ctrl-D. We've now defined the support positions, but nothing is visible in the 3D view apart from the path. That's because we have yet to define what type of supports we need, so over to the support types data form. As per the table, we'll select a V-shaped geometry, a normal stiffness of 1000 kilonewtons per meter, a diameter of 0.5, a length of 2 meters, and an angle of 30 degrees. Now we can see the supports appear in the 3D view. Before we leave this data form, just a note that, as with other objects, the shear stiffness is used in the friction calculation. We can optionally include friction with support both axially and laterally by adding a coefficient on the friction coefficients data form in the model browser. So let's run statics and see what happens. Not much. That's because the vital part of the process is identifying which line or lines we wish to be supported by this stinger. For that, we need to go back to the supports page of the vessel data form and select one or more supported lines. Now we should see a very quick solve, with the line immediately jumping to the correct side of the supports. We can see different colours for the supports in the statics complete state. Where contact is being experienced, the support is coloured white. These colours can be chosen on the support type data form. In the static state, the colours tell us that the first and last 2 supports have no contact, as they are coloured pink, and the remaining 5 supports are experiencing contact, as they are coloured white. Supports have their own result variables, so we can, for example, look at a static state result for support reaction force and confirm the presence of contact in, say, support 6 versus no contact in support 7. We select the vessel object, the static state, and then scroll through the variables to find support reaction force. When this is selected, we then need to identify which support we are interested in. I would like to compare 2 static state results, so I can select support 6 and click Show. Then hold the Control key while I do the same for support 7. They will then be displayed in one results window. And we can see a value for support 6, whereas support 7 has no contact and therefore has a value of 0. There are numerous other support result variables available to us, including support contact clearance, the distance between the supported line and the support roller, and support contact arc length, the arc length along the line that the contact is being experienced. I mentioned earlier that supports are useful for many other applications beyond pipe lay. If you would like to know more about some of these, there is a presentation on our website from a previous user group meeting in 2014. You will also find here a presentation introducing supports for pipe lay modelling. In addition, there is a video on our YouTube channel which gives some guidance on how supports can be used as a temporary aid to statics convergence. Finally, you can find more general information about contacting Orcaflex in this document available in the resources area of our website. Having spent some time looking at shapes and the various contact models in Orcaflex, our next video will focus on adding line attachments.